So, my dear friends, today I am going for the continuation of the previous problems, which are pretty important, my dear friends. This time I am covering not only the questions from 2000 up to 19, but I am covering up to the 2024 papers also, my dear friends, in the gate perspective point is concerned, my dear friends. Okay, so here very important. The continuation of the previous session is pretty important, my dear friends, over here. Okay, so in the today's class, I'm not only covering the problems based upon the semiconductor theory, but also few problems I'm going to cover, my dear friends, on the op-amps, and very important itself is that is the PN junction theory also. I'm covering certain points, my dear friends, over here in the today's class, my dear friends. Okay, let us begin the today's show. Okay, so here very important itself is that my dear friends, the question is that consider I had given a silicon sample doped with the Nd is equal to this value, that is 10 power 15 per centimeter cube donor atoms. Assume that intrinsic carrier concentration Ni, this is always the standard value, 1.5 to 10 power 10 per centimeter cube. If the sample is additionally, okay, so very important, that is if the sample is additionally doped with Na equal to 1 into 10 power 18 per centimeter cube acceptor atoms, the approximate number of electrons per centimeter cube in the sample at T equal to 300 degree Kelvin will be how much, my dear friends? Okay, that is very important, my dear friends, over here. Okay, so today's link, please drop cell one into our Telegram group also. The students are asking, someone is asking regarding that particular point over there. Okay, so this is the question, my dear friends, over here. Now he's asking the number of electrons, my dear friends, itself is that very important here. Okay, so very important itself is that see, very important, we have taken a silicon sample and it is doped with Nd. Whatever it is doped with Nd means it is forming like a N-type semiconductor. Okay, so if the sample is additionally doped with Na also means what happens, it forms like a p-type semiconductor, my dear friends. Okay, so very important itself is that I told you, when I'm doping here, when it comes to the doping level, see the doping levels of that is Na and here Nd, Na and Nd. But here what happens, the first conclusion itself is that the semiconductor is doped. We have the conclusion from this sentence. Okay, the semiconductor is doped with both acceptor and donor concentrations. Okay, with both acceptor and donor concentrations. Doped with what, my dear friends? Both the acceptor and donor concentration. Whatever it may, we have taken the Na value and Nd value. See here, Na value is much greater than Nd. Na value is much greater than Nd, my dear friends. Okay, this is the general parameter he has given, my dear friends, over here. Okay, now here ultimately Na value he only given over here, my dear friends. So here what happens, my dear friends, is that see, anyhow the silicon is doped with Nd, it forms like initially it forms like a Nd means N-type semiconductor, but additionally the sample is doped with Na atoms. So what happens, my dear friends? It is see, Na is greater than Nd means see, acceptor impurities are present. So here what happens? Hence it is becoming p-type. Hence it is becoming the p-type semiconductor. Okay, so if I am going to take it, my dear friends, first the he is asking the number of electrons. Okay, he is asking the electrons in p-type semiconductor. Okay, electrons, because it is the sample is additional doped with Na, so it forms like what, my dear friends? See, initially the silicon sample okay, is doped with Nd. It forms like N-type. But this N-type semiconductor additionally doped with again with Na, then it forms like a P-type semiconductor. And from the data also Na, that is the acceptor concentration is greater than the donor concentration over here. Okay. Now he is asking in the P-type semiconductor, he is asking the electrons in P-type. He is asking the electrons in P-type is equal to how much, my dear students, he is asking. This question is asked in GATE 2014 September 4. Go GATE 2014 September 4, my dear students. Okay. Over here. So here very important itself is that PP, which is equal to PP equal to Na minus Nd. Okay, Na PP, which is equal to Na value. So what is the value here? It is here. It is more. So we need to get that particular difference over here. Okay, which is very important, my dear friends. Over here, this is 10 power 18 and this is 10 power 15. Okay, so 10 power 15, then you are getting, my dear students, the value itself is 9.99 into, very important itself is that this is value I am getting, my dear students, in 10 power 17 per centimeter cube. You are getting, my dear students, this particular value over here. Now, as per the mass action law, what does the mass action law says, my dear friends? The mass action law says, very important itself is that in a P-type, P-type semiconductor, Np into Pp, which is equal to Ni square. Okay. Now he is asking Np. Np is equal to Ni square divided by Pp. So if I'm going to take it, very important itself is what, my dear friends, is equal to Ni square. Okay. Ni square by Pp, my dear friends. Okay. So already the concentration, intrinsic concentration is there and a PP value is there. Now substitute these particular values, my dear friends, you are going to get here. Okay. So Ni square, as usual, my dear friends, is equal to how much? That is, go for 1.5 into 10 power 10. Divided by PP. Okay. PP means then you are getting, my dear students, this particular value is approximately this value here. You are getting, my dear friends, this particular value over here. Okay. This is the answer, my dear friends. What he has expected. He has expected the answer. The number of electrons in the sample. Okay. In this particular sample, my dear friends, he has asked over here. Okay. This is the question. Next question. My dear friends, every time the questions are very tricky and answers are also like that, my dear friends, only. Now the question comes into picture in this particular question number 23 is pretty important, my dear friends, is that see how you are getting the values, my dear friends. Okay, see here. Now in this question, a silicon sample is uniformly doped with, here also donor type of impurities, means it is a N type of semiconductor of concentration is this one. The electron and hole mobilities of sample are 1200 and 400 respectively. Complete ionization of impurities. The charge of the electron is this one. The resistivity of the sample. The resistivity of the sample is how much, my dear friends? He is asking over here because here what happens? The silicon sample is doped with donor impurities. Donor. Donor impurities means it forms like what type of semiconductor? It forms like a N-type semiconductor. It forms like a n-type semiconductor, my dear students. Okay, very, very important here. Here, whatever the ND value. ND value, he only given, my dear students, is that this one, and mobility of electron mobility and hole mobilities, he only given. This is ND value. See here, if I am taking the value of this one, this is what electron mobility, this is whole mobility. He only given all these particular values, my dear friends, over here. And the charge, this is equal to Q, my dear friends. Now he is asking the resistivity. He is asking the resistivity of the sample, my dear friends. Okay, resistivity of n-type semiconductor. Okay, but we know, my dear friends, the formula for the conductivity. Okay, the conductivity is pretty, because he is asking the resistivity in n-type semiconductor is equal to how much. Okay, but I told you the conductivity in n-type semiconductor is equal to, what is the formula, my dear friends, which is equal to, I told you, very, very important, n into mu n into q. So here n is equal to nd, and it is equal to n equal to nd mu n into q, my dear friends. Okay, which is pretty, pretty important, my dear friends. Okay, if I am going to take it, very, very important itself is that the resistivity is asking. Resistivity is equal to the reciprocal of conductivity, which is equal to 1 by nd mu n into q, which is equal to which is equal to q, my dear friends, is equal to nd value. This here given, my dear friends, is equal to 10 power 16 into mu n, which is equal to 1200. Okay, the mobility of holes is not required. Okay, and it is equal to which is equal, how much the resistivity you are getting is equal to 0.521 ohm centimeter. You are getting, my dear friends, this particular value over here. Okay, this is about the question number, that is 23, my dear friends, and you are going to get the resistivity over here. How I have done, my dear friends, over here is a very, very important. Okay, similarly, question number 24. Okay, if I am going for the question number 24, very, very important itself is that, see, in the question number 24, see, he is asking, very, very important, see here, choose the right response from the question. An n-type silicon sample. See, my dear friends, when you are solving any particular question, you need to have the more idea, my dear friends, which is pretty, pretty important. More idea in terms of the first analyzing the question, my dear friends, and then you have to get the answer over here. Okay, which is equal to pretty, pretty important here. Okay, so the analyzing the question is pretty, pretty important. So what type of silicon? It is n type of silicon sample, is uniformly illuminated with light, which generates here 10 pi, that is equal to this sort of electrons has been generated. The minority carrier lifetime in the sample is equal to 1 microsecond in the steady state. The whole concentration, okay, in the sample is approximately 10 power x. What is the value of x? X is an integer. My dear friends, is asking this particular value over here. So here he has given an n type of semiconductor like this. N type of a semiconductor like this, my dear friends, which he has given over here. Okay, so this is an N type of semiconductor. In this N type of semiconductor, he has dropped the light. He has dropped the light here. Drop out the light here. On this N type of semiconductor, on this particular N type of semiconductor, then what happens, my dear friends, is that so it generates so that is 10 power 20 electron hole pairs. Electron hole pairs are generated per second. Per second, my dear friends. He only given this particular thing, my dear friends. Okay. So very, very important itself is that I told you, my dear friends, in the basic concepts, in that particular concepts, I told you the very, very important itself is that the generation rate formula, my dear friends. Okay. And that particular thing is also very, very important, my dear friends, over here. Okay. See, very, very important itself is that how the things are going to be generating, my dear friends, itself is that see, and that will be given by the time. Okay. So here the formula is equal to generation rate first. Generation rate, which is equal to, very, very important is that, say, is N type of semiconductor. N type of semiconductor means you are getting that excess electron concentration. Excess electron concentration by minority carrier lifetime. Minority carrier lifetime, my dear friends. Okay. Excess electron concentration, which will be, this is in terms of N type of semiconductor, this one. Here, in type of P, that is equal, formula is equal to tau P, and electron hole pairs per centimeter cube per second. Okay, this is what, my dear friends, you are going to get over here. So from this one, the generation rate, because here he has given the minority carrier lifetime. At the same time, my dear friends, is that he has given that you have to use this particular formula here. Generation rate is equal to, I am writing the generation rate is equal to GR, which is equal to delta P by tau P, my dear friends. Now he is asking the whole concentration. This thing, the whole concentration is equal to delta P. So here delta P is equal to generation rate into tau P. So what is the generation rate, my dear friends? Generation rate is approximately this value here. This is generation rate, GR. Generation rate. Okay. And here the minority carrier lifetime. The minority carrier lifetime is pretty important, my dear friends, is equal to, that is equal to this one, which is equal to, this is a tau P. Tau P. Okay. So here if I'm taking, my dear friends, that is equal to 10 power 20 into, my dear friends, is equal to 1 microsecond is nothing but how much, my dear friends, is equal to 10 power minus 6. So you are getting it is equal to 10 power 14, which is equal to 10 power x. He has given, this is the whole concentration is in given 10 power x. Then he is asking what is the value of x. What is the value of the x, my dear friends, he is asking. Then what happens to the x value? The x value equal to 14. The x value equal to 14, my dear friends. Okay. Like that, you are getting, my dear friends, the problem which I have done over here. Okay. Similarly, 25th question. This is somewhat, my dear friends, the tricky question that has been asked in the 2015 set number 2 over here. Okay. 25th question is also very, very important question, my dear friends. And how I'm solving the answer, that is also very, very important here. Okay. So that particular thing also I'm going to explain, my dear friends, over here in a detailed manner, my dear friends. Okay. See, very, very important itself is that, say, a piece of silicon is doped uniformly with the phosphorus with a doping concentration of 10 power 16 per centimeter cube. The expected value of mobility, here he has given the curve between the mobility and the doping concentrations for silicon, assuming full dopant ionization is shown below. Here in the curve, this is the dark line and this is the dotted line. The dark line indicates this is the whole line and the dotted line indicates here, sorry, this is the black line indicates electron and dotted line indicates the hole, my dear students, okay, which is very, very important over. And he has given the charge of the electron also over here. Now he is asking the conductivity of the silicon sample at 3. He is asking what is the value, my dear students. He is asking this particular thing over here. Okay, see, I told you very, very important itself is that he only given the silicon is doped with phosphorus. So phosphorus is a pentavalent impurity. Pentavalent impurity. So it forms like a what type of semiconductor? So silicon is doped with phosphorus, my dear friends, is that it forms like a what type of impurity? It forms like a N type of semiconductor. It forms like what, my dear friends, is that a N type of a semiconductor, my dear friends. Okay. And very, very important itself is that see from this particular question, what we have been concluded, say it becomes a N type of semiconductor. So the conductivity of silicon, he is asking, my dear friends, in N type of semi, that is silicon at a 300 degree Kelvin. The 300 degree Kelvin, my dear friends, is asking over here, okay, which is equal to, see, very, very important, my dear friends, is that that is what is the formula here? The formula itself is equal to Q into mu n into n, my dear friends. But here n equal to nd. N equal to nd, my dear friends. Okay. Then what happens, my dear friends? He only given, see here. Later I'm going to tell you each and everything over here. The conductivity is equal to Q into mu n into nd. Nd, my dear friends. He only given, my dear friends, over here. Okay. So we can take as per the graph. As per the graph, my dear friends, because here donor concentration is there. The doping concentration, this is nd is there. How much it is? 10 power 16. 10 power 16 is this one. So what is the corresponding mobility? Because mobility is not given. So from this graph, the corresponding 10 power 16, you are going to get the mobility. You are going to get the mobility, my dear friends. Okay. And that particular thing is very, very important, my dear friends. How much it is? See here. The mobility. See here. This is the mobility value. How much here? This is 1200. So for nd equal to 10 power 16 per centimeter cube. See here, for this one, the mobility, which is equal, how much, my dear friends, is equal to 1200. Okay. 1200, my dear friends, centimeter square divided by volt second. Divided by volt second, my dear friends. Okay. So what happens, my dear friends, is that very, very important itself is that, see, the conductivity, substitute here. The values already we got it, my dear friends. You need to substitute. Here the space is not enough. I am going to do, my dear friends, over here, which is very, very important here. So here, if I am going to substitute the formulas, in the formulas here, the conductivity, which is equal to Q into Nd into mu n, which is equal to, very, very important, my dear friends, is that Q is equal to Nd value 10 power 16 into mu n. Mu n is how much, my dear friends? 1200. The conductivity in a n type of sample is how much you are getting, my dear friends. When you are going to calculate, you are getting this value is equal to 1.92 units are ohm, centimeter inverse or Siemen per centimeter. Siemen per centimeter. You are going to get, my dear friends, these particular values over here. These particular values, my dear friends, you are going to get over here, which is a very, very important point. Just I would like to bring it to your notice, my dear friends, over here. Similarly, question number 26. So here, when I'm going for the question number 26 over here, and because the question number 25 is as usual, the parameters you got it over here. Okay. Now the question number 26 is the question that has been asked in 2015 set number 2 over here, which is very, very important, my dear friends, is that say in this particular question, he has asked here, very, very important is that the parameter of the electron current density. Electron current density, my dear friends. How to get that particular thing is also, I need to get the answer, my dear friends. Very, very important. This question is little bit of tricky and little bit of a big question. Okay. Now here, very, very important. The energy band diagram. And see, he has given the two profiles, my dear friends. Very, very important itself is that energy band diagram and electron density profile. NX in a semiconductor are shown in the figures. Assume that C has given this value Nx equal to this one. Okay. C has given the two profiles, my dear friends. One is this one, that is energy, that is band diagram. And second one is this is electron density profile. He has given in the two figures over here. Two figures. And he has given the Nx value and where alpha is equal to this particular value and X is expressed in centimeters and Kt by Q is this one and this is a value and D by mu is equal to this value and electron current density at X equal to 0. He is asking, my dear friends, let me do this particular problem in a detailed manner. So first of all, very, very important itself is that, my dear friends, is that two parameters are very, very important here. One is that he is asking the electron current density. Okay. Here, the two things are very, very important, my dear friends, is that after observing all the problem, problem in readable form and all those things, we came to our conclusion. What is that conclusion? Is that, my dear friends, is that that is very, very important itself is that see the electron current density is because of the both the currents, that is diffusion and the drift currents as usual, my dear friends, over here. But here completely, if I am going to do, very, very important itself is that how to get those particular values also, we need to check over here in a detailed manner. Okay. First of all, we need to check, my dear friends, very, very important itself is that the diffusion current and the drift current. Okay. Later, we are going to collect both the values here. So here, so we need to get the complete electron current density. Okay. The electron current density. The electron current density Jn, which is equal to, this is what, my dear friends, electron current density is because of one is diffusion, another one is what, my dear friends, is equal to, we need to find out both the currents, drift, diffusion and drift, my dear friends. Okay. Here, very, very important, first find out the diffusion, then we are going to find out the drift, my dear friends. Okay. First find out here. We need to find out the first one is the diffusion here. The formula for the diffusion is equal to dn by dx. Q into this one, my dear friends. Here n of x, which is equal to 10 power 15 u e power q alpha x by kt. This is n of x value, my dear students. You only given this particular value, my dear students, over here. First of all, I am doing one by one thing in a detailed manner. Put x equal to 0. So here, if I am substituting, my dear students, x equal to 0, then it becomes n of 0, which is equal to 10 power 15. You are getting, my dear students, for substitute here. Very, very important here. Then I am finding out the first one is the diffusion current. Then dn by dx. Now substitute here. This is dn of x divided by dx, which is equal to, this is 10 power 15 is 10 power 15, and this is e power. See, I'm doing for this one. Q alpha x divided by kt into q alpha by t. This is what, my dear friends, you are going to get here. Now substitute, my dear friends, over here in this particular thing. Very, very important itself is equal to t, because he is asking everything at x equal to 0. He is asking everything at x equal to 0. Then now substitute here, it is at x equal to 0. If I am doing, my dear friends, very, very important itself is equal to 10 power 15. Okay. Then e power 0. E power 0, it becomes what, my dear friends? 1. Then it is equal to, you are getting, my dear friends, is equal to q by kt into alpha. Okay. Q by kt. Q by kt is reverse. That is equal to kt by q is this one. Q by kt means reverse. Then it becomes what, my dear friends? 1 by 0.026. This is into alpha. Alpha value only given, it is equal to 0.1. 0.1, my dear friends. Then here, see, the answers are given. 4 answers are given, my dear friends. Leave it apart over here. Then you are getting dx at x equal to 0, which is equal to this, my dear friends. You are going to get, my dear friends, which is equal to, very, very important, my dear friends, how you are getting the value here. Okay. Now, my dear friends, I need to find out, very, very important itself is equal to this value. Okay. So, but I need to substitute, very, very important itself is that, see, all the parameters here. Okay. So, very, very important itself is dn value is missing. Dn value is missing over here. Okay. I need to find it because here q value is there. Dn by dx value, you got it, my dear friends. Now only see here, and dn is missing. Dn is here. Dn, see, dn value is, that is present, my dear friends, over here. Okay. Now see here. Now the formula I am substituting here, which is equal to, substitute this formula first, that is diffusion, this one, which is equal to the formula, that is equal to q into dn into dn of x by dx. So whatever it may be, the q value is equal to 1.6 into 10 power minus 19 into dn value. See here, the dn value is equal to this 36 and dn of x by this particular value is equal to, very, very important, is equal to what, my dear students, is equal to 3.846 into 10 power 15. So this value, you are getting the complete value is equal to 2.215 into 10 power minus 2, my dear friends, ampere per centimeter square. This is, you are getting only the drift, that is diffusion. Now I need to find out the drift because the two parameters are there here. One is diffusion, another one is drift. This is finished. Now I am going to find out this one. Okay. I need to find out, my dear friends, this particular thing over here. Okay. Drift, which is equal to n of 0 at 0 is asking. This is also at 0. Stated that. Okay. 0 into mu n into q into e. See here. He has given all the parameters that are mentioned, my dear friends, over here. So, okay, don't get confused how we are getting those particular values also, which is pretty important, my dear friends, over here. Okay. So, we need to get those particular values because dn is there, but there is no mu n here. So, there is no mu n, my dear friends, over here. How to get that particular value also, I am going to tell you, my dear friends, which is equal to very important here. Okay. Here, the slope value also he has given, E value. This is E value. Now see here. First find out here, mu n. I told you dn by mu n. dn by mu n, or which is equal to 1 by Vt. I need to find out mu n. Mu n. If I want to get mu n, or we can take it as, my dear friends, very important. I need to find out the parameter for, okay, dn by mu n, which is equal to Vt. So mu n is equal to dn by Vt. Already dn value is there. Okay, that is 36 and Vt value is there 0.026. You are getting the mu n value, which is how much you are getting is that, what is the value you are getting, my dear friends? 1384.8. This is so already you are getting the mu n value. In the previous case also, you got it, my dear friends. Very important here. So this is the value, my dear friends, you are going to get over here. Okay. So very important is that this is the value. Now substitute this mu n value here, and energy. I told you this value of the energy is here. This is the value. Now substituting all the parameters. Now here, and my dear friends, the E value is negative here. E value is negative here. Now substitute here. Drift, which is equal to N0, mu n, q, and E values you are getting, my dear friends, which is equal to 10 power 15 into mu n value 4.8 into charge into E value minus 0.1. Then you are getting, my dear students, this value is equal to minus 2.215 into 10 power minus 2 ampere per centimeter square. This is now what is the formula for complete Jn? Jn is the combination of this is 1. This value you are going to get itself is 2. So 1 plus 2, 1 is positive and 2 is negative. Then you are getting this value equal to 0. This value equal to 0, my dear students. Okay. Which is equal to 0, my dear students. You are going to get this particular value here. This is what about, my dear students, how I done the problem. So this question has a little bit of tricky enough over here and a little bit of 2 marks question. This is asked, my dear students, in the previous paper. Now question number 27. If I am going for the question number 27 is also very, very important. And the 27th question, okay, is also sometimes that has been asked in a model problem, which will be 2015 model problem. So how to do this particular thing is also we are going to see over here. Okay. So see here, a DC voltage of 10 volts is applied. This is a N-type silicon bar. 10 volts is applied. A rectangular cross section of length 1 centimeter as shown in figure. The donor doping concentration ND and mobility of electrons. These are the values, my dear students, he has given respectively. The average time taken by the electrons to move from one end of the bar to the other end. So he's asking, my dear students, itself is that the time. What is the average time that is taken, my dear students, from this particular bar that is moving from this end like this? He is asking, my dear students, over here. Okay. He has given L value, the length 1 centimeter. He only given. Okay. And mu n is equal to mu n value is equal to 1000 centimeter square per given, my dear friends. Very, very important itself is that this mu n value and nd value is equal to 10 power 16. He only given this value per centimeter cube. He only given all these particular values, my dear friends, over here, and voltage V equal to 10 volts. He has given these things over here. Now, first of all, before finding out the time here, it's a N type of semiconductor. Let the velocity of electrons traveling here. The velocity of electrons is equal to, very, very important itself is that. First of all, let me find out the very, very important here. The parameter itself is equal to the E value. Okay. The electric field here. Because I told you, very, very important itself is that we need to find out the importance value here. So velocity of electrons because in this bar, velocity of electrons V is equal to mu n into E. V is equal to mu n into E. E is equal to V by L. 10 volts by length is 1 centimeter. Here you are getting this is 10 volts per centimeter because we are getting this value only. E, you got it, my dear students. Now substitute here because mu n is there here and E value is there. Now we need to find the velocity. Velocity V is equal to which is equal to 10 power 4. This is the value, my dear students, we are going to get here. Velocity. But velocity is equal, what is the formula, my dear students? Distance by time. Now he is asking what is this time t. T equal to L by V. T equal to L by V, my dear students. Okay. Then here T equal to L value 1 centimeter by velocity 10 power 4. Then you are getting, my dear students, this particular value is equal to how much is 10 power minus 4. Can I write down this 10 power minus 4 in terms of very, very important is that 100 microseconds as absolutely can I mention like this. I will mention, my dear students, like this over here. So this is about the next question. Here the time itself is that the average time taken itself is equal to 100 microseconds. Next problem. Now, my dear friends, I'm going for the question number 28 here. Okay, which is pretty important, my dear friends, is that how to solve this particular question also. Very, very important here. Okay, and how to execute this particular problem here. Now, see here in the question. Say, a small percentage of impurity is added to the intrinsic semiconductor at a 300-degree Kelvin. Which of the following statements is true for the energy band diagram in the figure? Conduction band and valence band and the new energy level. This is conduction energy level and this is the valence energy level. So here the new energy level is near to the 0.01. Here this is the new energy level. Okay. See here, very, very important itself is that, my dear friends, which of the following statements is true here? He is asking, my dear students, is that very, very important itself is that, see what type of, first of all, let me identify that this is the very, very important itself is that intrinsic semiconductor doped with the pentavalents to form a n-type semiconductor, it is okay. Intrinsic semiconductor trivalents to form a n-type, okay. So this is to form a n-type, this is wrong, leave it apart. Okay, here he is asking, my students, the intrinsic semiconductor doped with pentavalent. Okay, if pentavalent, it forms like a what, my dear students? This is also wrong here. Intrinsic semiconductor doped with trivalent atoms to form p-type semiconductor. Okay, so now, my dear students, okay, this statement and this statement, n-type and p-type is right only. But here, the question itself is that here, whatever the Fermi level that is present, this Fermi level is near to the conduction band. So this Fermi level is near to the conduction band in which type of semiconductor? In n-type of semiconductor. In here, this is what, my dear students, the Fermi level is near to the conduction band. So in n-type, because in n-type semiconductor, the Fermi level is near to the conduction band. Okay, the Fermi level is near to the conduction band. So in p-type semiconductor, EF means Fermi energy level. Fermi energy level is near to the valence band. Near to the valence band. So here n-type semiconductor, this one here. So option itself is what, my dear students, among these options, because the Fermi level is near to the conduction band, means the option A itself is right. Okay. If this particular Fermi level is present over here, then it could be the answer D should be right. 29th question. This is also page number. We need to solve, my dear friends. Very, very important itself is the this particular thing over here. Question number 28. 28 or 29? This is. Now I am going for the question number 29 here, which is very, very important, my dear friends. Itself is that over here. Now see here. He has given the question and we need to check the question and we need to get back the answer, my dear friends, over here. He has given the 4 options also, which are very, very important here. And we need to get the different answers over here. See, he has given the 4 options here. See, consider a silicon sample T equal to 300 degree Kelvin with a uniform donor density. Nd is this one, illuminated uniformly, such the optical generation G opt is this one throughout the sample. Okay, this is what, my dear friends, is that see, I am projecting the light optical. This is optical light over here is G opt, that is equal to, my dear friends, that is throughout the sample. This is a silicon sample. Silicon sample. Here, the incident radiation is turned off at T equal to 0. Now you can turn off at this time. Assume low level injection to be valid and ignores the surface effects. The carrier lifetime TPO, this is a value, and lifetime for the holes and electrons is this value. The whole concentration is T equal to 0 and the whole concentration is at this particular values are how much, my dear friends, is asked. He is asking, my dear friends, these particular values over here. Okay. Very, very important, my dear friends. I have been to tell you the formulas. The formulas are very, very important here. And I have been derived those particular formulas in the general classes. Okay. So in that, I am going to do, my dear friends, is that very, very important here. Okay. That is equal to Pn of t, which is equal to P dash. This is the expression. Already we have done, my dear friends, this particular expression 1 by tau p here. Okay. Low level injection. Low level injection. So under low level injection, this term is ignored. This particular term, sorry. In this expression, this particular term is ignored. This particular term is neglected. Then what happens, my dear friends, is that first of all, we need to find out this. There is a separate formula for this one. That is equal to which is equal to G opt into tau PO. G opt, which is equal to this value here, already it is there. And tau PO value is here, my dear friends. Now substitute these values here. Then it is what, my dear friends, you are going to get itself is. This is what, my dear students, you are going to get. Substitute at t equal to 0. If you are substituting, my dear students, very, very important itself is that in the expression, my dear students, I am going to substitute because this is neglected. When this is neglected means this term has been moved out. Now in the expression 1, my dear students, is that substitute in this particular expression, substitute. See where you are getting the value. This is here. This is t by, sorry, where the t term is there. Here t term is there. This is t. That's the reason I am t equal to 0 here. Now I am substituting here. The term is very, very important itself is that Pn of t, which is equal to Pn dash of O e power minus t by tau p. This is the expression. So in this particular expression, substitute. What are the expression I got it here? Once I am writing, my dear students, here. Because the second term is neglected. Then it becomes this value. E power, very, very important is that minus 0. So whatever the value you are getting is same. So P n dash of O, already you got this value. See here, 1.5. Into 10 power 30 per centimeter. This is what, my dear students, we are going to get the value here. Okay. Now, at t equal to 0, this is at t equal to 0. Two conditions they are asked. One is at t equal to 0. This is finished. Next, again, is at t equal to this one. 0.3 microseconds. Microseconds, my dear students. Then what happens? See, the parameter has been changed over here. P n of O, which is equal to P dash of NO into e power, my dear students, is equal to 0.3 divided by 0.1. Then it is how much? 7.47 into 10 power 11 per centimeter. This is what, my dear students, you are going to get these values over here. Okay. So what is the option, my dear students? Already see the two values are there. One is this value and another one is this value. So the option is here. A. The option itself is A, my dear students, which is a pretty, pretty important point. Just I would like to bring it to your notice, my dear students, over here. Okay. Next problem. Is question number 30. See here also, there are certain parameters, my dear friends, we need to check out over here, which is very, very important here. Okay. And in the question number 30, if I am going to solve, very, very important itself is that, say, how the parameters are changing here also is very, very important, my dear friends. We need to check this particular answer also over here in a detailed manner. See, this is somewhat a big question. See here, the figure shows the doping distribution in a p-type semiconductor scale. This is the magnitude of the electric field in a semiconductor due to the non-uniform doping. Non-uniform doping, my dear friends. Okay. Say this is what type of semiconductor you only mentioned. It is a p-type of semiconductor. It is what, my dear friends, is that see, here very, very important itself what kind of doping he has done due to non-uniform doping. Due to non-uniform doping, diffusion exists, but the net current should be zero. Diffusion exists, but the net current should be zero, and hence, and the drift current opposing diffusion should be exist. Okay, here very, very important itself is that the net current is zero, but the drift current is opposite to the diffusion current in p-type semiconductor. So here, due to the non-uniform doping, this is a p-type semiconductor. The current density equal to 0. So this current density value 0 is equal to what are the value you are getting is the p-type semiconductor, which is equal to minus q dp into dp by dx. This is what, my dear friends, is that this is equal to drift. This is equal to diffusion. This is drift and this is a diffusion, my dear friends, which is very, very important, my dear friends, over here. So here, yet another important point also, we need to get back, my dear friends, which is equal to very, very important here. Okay. So how the things are there? This is the complete scale. This is the micrometer scale, and this is the acceptor concentration scale. Here, this is what kind of scale? It is a logarithmic scale. This is what scale? Logarithmic scale, my dear friends. He only mentioned over here. Okay, which is very, very important, my dear friends, over here. Okay, so generally there is one more formula. I told you, my dear friend, for the E, that is the energy formula. E equal to, this is formula 1. E equal to Vt by P into dp by dx. dp by dx, my dear friends. Already I told you the formula for dp by mu p equal to Vt. This is also I told you, my dear friends, in your last class. Okay. So already we have done some problems, and we are also P equal to Na. P equal to Na, my dear friends. Okay. So substitute here in terms of this one. Now I'm doing, my dear friends, this particular problem in the next. Here very, very important itself is that E is equal to Vt by P into dp by dx. Okay. Here P equal to Na. P equal to Na, my dear friends. Then what happens? E is equal to Vt by Na into dNA by dx. dNA by dx, my dear friends. So here E is equal to, see here what happens? This becomes Vt becomes Vt. So 1 by NA into DNA by DX. This term I will write down, my dear friends, like this. In terms of what, my dear friends, are very, very important, because I have represented this term can I write down, my dear friends, d by dx into ln Na of x. Can I write down, my dear friends? Very, very important itself is this one. Okay. So if I'm writing, my dear friends, this particular term is like this. Okay. Now, my dear friends, I'm substituting here. What are the values you are going to get? Those particular values are pretty, pretty important, my dear friends, over here. Okay. So, and we need to get those particular values also over here. Okay. Now, my dear friends, at 2 points, one point is here and another point is here. Okay, this is with respect to the scale. Okay, so the distance in between the scale, in between the distances, my dear friends, over here. This I am going to call it as x1. This I am going to call it as x2. Okay, because in between those particular parameters also, I am going to write down that particular formula, which is very, very important, my dear friends, over here. Okay, and we need to substitute those particular values over here. Okay, then only you are going to get those particular things, my dear friends, over here. Okay, now here from this particular formula, I'm writing here in the next page. Say this value E is equal to VT into ln of, here very, very important itself is that what are the values I'm going to get is pretty, pretty important. And those particular values also we need to write down over NA2 minus ln of Na1. Okay, which is pretty, pretty important, my dear friends, is that so we need to represent, my dear friends, is that very, very the values. Okay, the values I'm representing, my dear friends, is pretty, pretty important over here. Okay, so how I'm representing those particular values also, I'm writing, my dear friends, over here, which is equal to, on the denominator, it will becomes log 10 base. Okay, or we can say simply, my dear friends, itself is that I am writing the parameters which are. See here, very, very important itself is that log 10, okay, log 10, and this value is equal to x1 this value I am representing, my dear friends, in a different manner. This is the value I am representing, my dear friends, in a different manner over here. Okay. So how we are getting this particular value over here. Okay. So whatever it may be, I'm using or simply this particular value I am representing in terms of x1 and x2. X1 and x2, my dear friends, I am representing, or I can simply write down here. Simply, this is x2 minus x1, x2 minus x1, my dear friends. Okay, then it will be VT, which is equal to Na2. So here where you are getting, my dear friends, ln values and all those things over here. Okay, so what are the value? NA2, NA1. So all these particular parameters are very, very important, my dear students, is that and those particular value also we need to substitute, my dear students, which is equal to very, very important, my dear students, because we are going to find out at 1 and 2 at the same time. See here, this is in between the distances. See here, due to non-uniform doping at 1 and 2. 1 and 2, that is what, my dear students, is this one. And second time, if I am going to use, very, very important itself is that, see, the non-uniform, that is non-uniform doping level. If I am going to do this particular parameter, two things are very, very important here. Okay. One, I need to find out the value exactly at VT. Okay. Second one itself is that, see, the question you only given, see here, non-uniform doping. So how you are getting those particular values also here? He has not given the options over here. We need to do directly, my dear students, over here. So LN, okay. So whatever it may be the value, LN, NA2 and NA1. NA2 is here. This is NA2. NA1. NA2 and NA1. And this is X2 minus X1. So here, before this particular point, my dear students, I am writing, don't write, directly write over here. Now I am going for log 10 of x1, which one equal to 1, which is equal to x1 equal to 10 micrometers, which is equal to 0.001 centimeter. So here x2 becomes 100 micrometers, because he has given, my dear students, all the things in here in micrometers only. Or you can change, my dear students, in the form of centimeters if it is needed. Okay, then it will be 0.01 centimeters. So here ln of 16, which is equal to 36.84, ln of 10 power 14, which is equal to 32.24. This is what, my dear students, over here. Okay. So very, very important itself is that, my dear students, is that say these values over here. We have written these particular values, my dear students, over here. So I am doing now, substitute what are the values in this particular formula. Then you are getting, my dear students, the value itself is that very, very important is the value that we need to get over here. Okay. So that particular thing I am going to do over here. Therefore, E is equal to 0.26. That is 6.84 minus 32.24, because the values already you are getting divided by. I am converting, my dear students, in the form of centimeter, 0.01 minus 0.001 centimeter. Sorry, this. Then close this bracket. Which is equal to 0.0133 133 kilovolts per centimeter. Kilovolts per centimeter. Like that, my dear students, you are going to get the answers over here, my dear students, in this particular fashion. Okay, this is see here how the question will be completely. We need to get back all the values here. This is a NA2, NA1 value, X2 value, X. Get it back all the values here. So then we need to find out the values here, and finally you are going to get the answer over here like this. Next, question number 31. So here also, this particular question is very important, my dear friends. See, and this particular question is little bit of, okay, the tricky question. Okay, little bit, not a big bit, my dear friends. So how to solve these things is also very important, my dear friends. Okay, see here, very important is that question number 31. Okay, the IV characteristics you only given. The IV characteristics of three types of diodes at room temperature are X, Y, and Z, as shown in the figure. Diodes are uniformly doped and identical in all aspects of their particular material. XYZ are the semiconductor material. EGX, EGY, and EGZ are the band gaps of X, Y, and Z respectively. Then, my dear friends, say here IX, IY, and IZ. This is asked by dear students over here like this. Now, what is the options over here? So, what is the energy gaps here? Okay, three semiconductors he has taken, my dear friends, itself is that very important, my dear friends, is that if I am taking this particular diode, see here, made of three types of diodes made of the three semiconductors. Okay, and the cut-in voltages, if I am taking the cut-in voltage of this particular diode, which is very important, my dear friends, is that say cut-in voltage. This is V gamma 1, V gamma 2, and V gamma 3 are the cut-in voltages, my dear friends. Very important here, where cut-in voltages. See here, my dear friends, in the cut-in voltages, the order of priority itself is that this is order of priority. Order of priority as this increases, my dear friends, as the energy gap at 0 degree Kelvin increases, then intrinsic concentration decreases, my dear friends. Then I told you, my dear friends, is that the cut-in voltage formula, the cut-in voltage which is equal to KT All these things have been derived in the NA ND divided by Ni square. Ni square here. So when I'm taking, my dear friends, the relations very important itself is that see, when this one is increasing, this one is decreasing. So the relations itself is that, my dear friends, is that there will be a direct relation between the cut-in voltages directly proportional to the EG. So very important itself is that, see, when there is a direct proportionality in terms of EG also, so EZ is greater than EZY is greater than EGX, because this is the third one. Third indicates Z term, two indicates Y term, one indicates X term. So answer is what, my dear friends, is that what is the answer? The option C. The option is the C, my dear friends. You are going to get the question over here. Next, question number 32. Okay. So this is also very, very important, my dear friends, when I'm going to do the question over here, which is very, very important, my dear friends, is that how I'm doing this particular problem. This is a basic question. This is a general basic question which has been asked, my dear friends, in the previous paper. Okay. So here also, if I'm going for this particular question, okay, very, very important itself is that how to, okay, do this one. A bar of gallium arsenide is doped with silicon such that silicon atoms occupy gallium and arsenic sites in a GaAs. Which of the following statements is true? See, I have taken a bar of gallium arsenide. This is a bar of gallium arsenide. Is doped with silicon. Now I have done the doping with silicon. See, silicon atoms occupy gallium and arsenic sites. Okay. So here silicon atoms occupy, my dear friends, is that very, very important itself is that occupy gallium and arsenic sites in a GaAs crystal. Okay. GaAs crystal, my dear friends. Okay. Now, here very, very important itself is that see, a very, very important itself is that see, very, very important itself is that see, it occupies gallium and arsenic. So then it doping will be done over here. So here this particular diagram will be forming like this. It's completely a bar. This is also a bar. So here what happens? The gallium arsenide so here gallium arsenide by silicon atom. Okay. So what happens, my dear? Gallium site replaces by, when I've done, the silicon is doped here both with doping with this one, the same here, that is doping with arsenic also. So gallium arsenide, and my dear friends, is that by the, here what happens? It is gallium site. Here what happens? Gallium site by silicon atom produces, okay, free electron of n type. Next one is arsenic site with silicon atom produces whole free holes of p type. Free holes of the p type, my dear friends. Then ultimately, what is the option, my dear friends, itself is that here silicon atoms acts as a p type dopant in arsenic sites and n-type dopants in gallium sites. This is right only. Why means here acts as a, here p-type dopants in arsenic sites and here n-type dopants in gallium sites. This is what, my dear friends. So option is this one. The rest options are wrong here. Question number 33. Page number 2, right there itself is that very, very important. But the 33 question. How to do this particular problem also, my dear friends, let me explain over here in a detailed manner. Okay. See here. Wait a minute. See, my dear friends, the dependence of, in this is 2017 question, the dependence of the drift velocity of electrons on electric field in a semiconductor is shown below. The semiconductor has uniform electron concentration of N equal to this one, electronic charge, and a bias of 5 volts is applied across 1 micrometer region of this semiconductor. The resulting current density in this region is how much, my dear friends? This is very, very important, my dear friends, over here. Okay. So, this is the things he has given, my dear friends, which is very, very important here. So, 5 into 10 power 4. Now, my dear friends, is that we need to check very, very important itself is that what kind of, that is the resulting current density is asking. First of all, let me find out the very, very important itself is equal to the electric field. Electric field is equal to V by D. V, the voltage, V equal to, very, very important itself is what, my dear friends, is equal to the voltage V is 5 volts divided by D, distance. Distance is equal to see any distance as he has given across 1 micrometer region here, D, this is D. D here. V is here. So it will be 5 by, so it will be 5 into, convert into centimeters. 5 into 10 power 4 volt per centimeter. This is what here. Okay. See, now my dear friends, see, he is asking, so as the electric field is this value, see here, as electric field is 5 into 10 power 4 volt per centimeter, this value. So means it is at, this is electric field is, this is E value. So if it is at 10 power 5 is this one, if it is at 5 into 10 power 4, then what is the value, corresponding value? What is the corresponding value, my dear friends, for the drift velocity? The drift velocity, the corresponding value is equal to, this is 10 power 7 means this is equal to 10 power 6. If it is 5 to 10 power 5 is this value, 5 into 10 power 4 means this 10 power 6 value. Okay. This is what here, my dear friends. Okay. So this is a value, and VD equal to 10 power 6 centimeters per second. Okay. This is what here. Then substitute the current density. J is equal to rho into E. Then it will be N into Q into, this is a value here. But what is this value? This is nothing but N Q into, this is nothing but VD, drift velocity. So the N value, he has given any concentration for a doping here. The response, this is the drift velocity, VD value. That is okay. But what is this value of N? Okay. The N value, he has given the concentrations here. This is N value. N value is here. N value is here, my dear friends. Okay. Which is very, very important, my dear friends, is what is the N value? N value is here. That is 10 power 16. Into Q value. Q equal to 1.6 into 10 power minus 19. And VD value. VD is this value. This is corresponding to the, my dear friends, 5 into, because we got the electric field is 5 into 10 power 4. The corresponding value for 5 it is 10 power 7. 5 into 10 power is this 10 power 6. Okay, then it will be 10 power 6. Then it will be very, very important itself is 1.6 kilo ampere per centimeters. This is what, my dear students. See, this is what, my dear students, how you got the answer over here. You just check it. First, find out the electric field. Then electric field, the corresponding electric field, the corresponding drift velocity, got it. Now current density, because what type of semiconductor it is a N type of, okay, the general N type of semiconductor, in that the formula for the current density is equal to this one, the conductivity into U, the conductivity formula is this one into E, okay, which is very, very important. Okay, in this, what is mu n into E is nothing but drift velocity. Now substitute here. Okay, you are going to get this one, my dear students, over here. Similarly, next question. The question number itself is the 34 question, my dear friends, which is also very, very important here. See here. This is a uniformly doped silicon bar of length 0.1 micrometers with a donor concentration Nd is equal to this one, is illuminated at x equal to 0, such that electron and hole pairs are generated at the rate of this value, GL equal to this one. So in between the values of 0 and L, okay, where GLO is equal to this value is given. Whole lifetime is this one. Electron charge is this one. Hole diffusion coefficient dP is this one. And low level injection prevails, assuming that linearly decaying steady state excess hole concentration that goes to 0 to x equal to L. The magnitude of current or diffusion current density at x equal to L by 2. At x equal to L by 2 is how much, my dear friends? He is asking this value over here. Okay. So here the light is projecting over here. The light is projecting on this particular what type of silicon bar? It is a nothing but a silicon bar N type, because Nd concentration. N type silicon bar. Okay. In this N type silicon bar, if I am taking, my dear friends, is very, very important itself is that say only the light is projecting on this one. So I told you, my dear friends, the expressions for these things in my theoretical classes. Okay. So there also very, very important, my dear friends, the points we need to write down over here. First of all, dP, diffusion constant for holes, only given here, that is equal to 100 centimeters square per second over here. Very, very important. And J, okay, N of X. Because this is what, my dear friends, is that with respect to the only, because here what happens in this particular semiconductor, which one is, my dear friends, very, very important itself is that say the diffusion of what, my dear friends, the diffusion of the p type, okay, whatever it may be, you are getting itself is dp into q into dpx by dx. Okay, this is what here the prevailing conditions, my dear friends, over here. Okay, and my dear friends, is very, very important. He has given the p of x value also, that is equal to g of LO into 1 by x minus L into tau p1. Tau p1. This is a formula. This is another formula, my dear friends, have been described over here. Okay. So these things also, if I am doing for this expression here, because dp by dx we need to do. So it will becomes GLO into minus 1 by L into tau PO. Tau PO my dear students, you are getting, my dear students, over here, which is equal to, very, very important itself is that this is the, because here ultimately we are getting this particular term, my dear students, but substitute this particular term here. You need to substitute, my dear students, this particular term over here, okay, which is very, very important, my dear students, over here, okay. So then you got the DP value is there, which is very, very important here. You got this one, and you got the value of that is what, my dear students, is the value which is very, very important. Now substitute this value here. I am writing in the next page directly. So here that is completely J value, which is equal to because formula itself is dP into Q into dP of x by dx. But anyhow, my dear students, we got this value. This is also negative. Their negative is there, then it becomes positive. We have the values of GLO, all these values are there, TPO, all these values are there. Now I'm substituting, my dear students, those particular values are here, which is equal to minus and minus, it becomes plus because one minus is there in the dP by dx term into 10 square dP value and a charge. This is charge is equal to into dP x value, which is equal to dx is equal to, see here, this value, tau PO. What is the tau PO value? See here the values you are using, my dear students. This is here value you are getting, my dear students, is 10 power 13 into 1 by L. Into 1 by L, my dear students. Okay. Here he is asking, already given the value of L also. L is at 1, that is L by X is L by 2. So what happens, my dear students? See here, very, very important itself is equal, L is equal 0.1 micrometer. Then L becomes 10 power minus 5 centimeters. Then you are getting, my dear students, is that J value, which is equal to, very, very important itself is that 16 ampere per centimeter square. Like that, my dear students, you are going to get the answers, my dear students, over here. Okay. So these are all the important formulas just have been depicted, my dear students, which are very, very important over here. Okay. Similarly, I am going for the next problem. Let's take break for 2 minutes only. Next question. So choose the right response from the questions, my dear friends, which is very, very important here. How to get the answers for this particular question over here. Which of the following options is correctly describes the equilibrium band at T equal to 300 degree Kelvin of silicon, P, N, N plus, and P double plus. P means normally doped. Normally doped P, normally doped N. This is heavily doped and this is very heavily doped configuration. The equilibrium band diagram. The equilibrium band diagram, my dear students, over here is very, very important. First, the thing itself is that whatever the question he has given itself is that there is no, for this semiconductor, there is no biasing. Okay. So hence, Fermi level should be constant. Okay. See, for this diagram, the first thing itself is that no biasing. No biasing indicates no Fermi level. No Fermi level, my dear friends. Okay. And very, very important itself is that I would like to bring the very, very important things over here in the four regions of P, N, N plus and P plus. What happens, my dear friends, is that in P type of semiconductor, I told you Fermi level always is closer to, because in P type semiconductor, always I told you, my dear friends, in the last class, in the today's class only, not last class. In P-type semiconductor, the Fermi level is close to always. Fermi level should be close to EV. Close to EV. And in N-type semiconductor, you know that Fermi level is close to EC, my dear friends. Very, very important itself is that in N plus, because this is finished, this is finished. Next, I am going for N plus and P plus plus. In N plus plus, my dear friends, is that first one is I am going for N plus, later I am going for N plus plus. Sorry. Let me finish about the third part. First part is finished, second part is finished, third part. In N plus semiconductor, Fermi level should be still closer to EC, edge of the conduction band. Edge. N plus means Fermi level is close. Still close. Edge of the conduction band. And N plus plus, Fermi level penetrates into valence band because not in valence band. So, what is the option, my dear friends? He has given the four options here. Options that are varying. One is option A, option B, option C, and option D. Over here, the correct option, if you are seeing the C here, option C. Why means here very, very important, my dear friends, is that C. If I am going to take it, the conduction band and valence band, see here, I told you in P-type semiconductor or N-type semiconductor, very, very important itself is that in P-type semiconductor, Fermi level is close to valence band. Okay. In N-type semiconductors here, Fermi level is close to N-type or P-type. In P-type. In P-type semiconductor, this is here. In N-type semiconductor, the Fermi level is close to this one. I told you, my dear friends, at another important point is that in N plus type, Here n plus type, my dear students, is that see, it is here, my dear students, is that it is touching the various values. It is touching, my dear students, itself is that very, very important itself is the values over here. Okay, how it will be taking place over here. So this final one is, sorry, this is P plus plus. Sorry, my dear students. That's what I am getting doubt here. P plus plus here. That's what I'm getting, my dear students. Don't doubt over here. Now the option itself is this is the wrong option, my dear students, over here. The options we are going to get is very, very important, my dear students. How you are getting the different options here? Okay, because this question is asked in 2019 paper. Nowhere, my dear friends. This is the right option here. Option D. Sorry for that, my dear friends. See here. See here. This is the Fermi level at the center. This is conduction band and this is the valence band, my dear friends. In N-type semiconductor. Okay. In N-type semiconductor, my dear friends, see here. I am going to tell you one by one. The Fermi level is close to the here in P-type semiconductor. This particular Fermi level is close to over here. NP or Pn plus P. Whatever the things he has got is P. See here P. N, four options. N, N plus and P plus. P plus plus. Like that, he has given the four options here. P, N. See in P type. If I am taking the P type for Fermi level should be close to EV. Yes, my dear friends, is that see it is very close. Okay. The Fermi level is close to in where, my dear friends, in P type. See here. In P type. Next is in N type. Fermi level is close to EC. In N type. This Fermi levels here is close to N type. This is. Now, if I am going for in N plus type Fermi level, should be still close to EC. In N plus type Fermi level, should be close to EC. See, anyhow, it is going for N plus type. And third one is P plus plus. See, the Fermi level penetrates into valence bands here. Like this. So option itself is D, my dear students. Okay. You are going to get the option, my dear students, over here. Okay. Similarly, I am going for the next question, my dear friends, which is very, very important, my dear friends, itself is that see how you are getting the various values over here. Okay. Now here, consider the recombination process. This is a circuit here. Via bulk traps in the forward biased PN homojunction diode. The maximum recombination is Umax. If the electron and hole capture cross sections are equal, which of the following statements is false? Which of the following statements is false, my dear students? Okay. See, very, very important itself is that we need to take the relative distance through that is charge space region. Okay. And we need to take it with respect to the various important parameters, my dear students. So which of the following statement itself is false is asking among these particular things, which is in GATE 2020. So we need to get back one thing important. See here. This is the curve already been explained in your theoretical class. This is relative recombination rate on the y-axis. And here, relative distance to space charge region. Okay. The maximum recombination rate, Umax, does not occur at the edges of the depletion region in the device stored. So here what happens, my dear students? First question. See, Umax is what, my dear students, is the ultra max. Okay. Umax occurs at the see here. What are the Umax? That is what, my dear students, is that the maximum recombination rate. See, suppose this is if I'm taking, my dear students, charge space region, the depletion region will be either sides. It will be present, my dear students, on the either sides over here. Okay. Which will be on the either sides. Okay. So very, very important. Umax occurs at the edges of the depletion region in the device. So very, very important itself is that see which of the following is a false statement. Okay. False. Okay. Umax, very, very important itself is that depends exponentially on the applied bias. Next one is with all the parameters you unmax here. Umax decreases if the intrinsic carrier density is reduced. With all the parameters unchanged, Umax increases if the thermal velocity of the carriers increases, my dear students. Okay, whatever it may be. The question itself is what, my dear students, is that a little bit of tricky over here. Okay, we need to check again the question parameters here. Okay, very, very important here. Okay, and that particular thing is very, very important here. So always Umax, okay, occurs at the edges. Okay, very, very important of the depletion region. Okay, Umax occurs. This is statement is false. Umax does not occur. See here, it occurs in the charge space region. Umax occurs in the charge space region. Charge space region only it is occurring, my dear students. Okay, it is occurring, especially, my dear students, very, very important itself is that in the charge space region, my dear students, where it is occurring. Just I would like to bring it to your notice, my dear students, over here. Okay, this is the general parameters, my dear students. I would like to bring it to your notice over here, my dear students. Okay, so anyhow, Selvan, we have completed the today's the class, my dear students. Anyhow, the students who has kept your continuous efforts in uh, writing your particular examination, especially the pretty important things I would like to bring it to your notice when comes into the examination point itself is that see, because you have only the 1 week is left for your particular gate examination. Okay, and the pretty important thing I would like to bring it to your notice itself is that see, every time you are preparing for the examinations, but here the gate examination is quite different from your general engineering examinations. Here, the concept, the formulas, and the calculation speed also we need to maintain, because the gate examination is a little bit of the tough examination when compared to the other examinations. So first of all, while going for the examination, every subject you write down all the formulas in the blank pages. Okay. The second thing itself is that the formula remembrance is quite important. There you won't get more time to solve. So you have the very less time. So for every student, those who has attended my classes, my dear friends, okay, that is Alekya, Selvan, Anant, Yogalakshmi, Harita, every student, Durga Prasad, every student, my dear friends, I am saying only one thing for all of you. All the best for your particular gate examination, which is going to come in the next month, that is in February, because today is the last, that is a January. I kept my efforts in teaching the subjects of EDC and analog. Hope you have all expected what the things have been done, my dear friends. But the thing itself is that you need to keep on your efforts till the completion of your examination, and all the best for your exam, my dear friends. And
Sir,
thank you very much. Selvan, boliye.
sir, can you share the notes?
Yes, definitely I will share it. Okay. And Selvan, one more
Okay.
important thing to you. I told you one important thing before going for the exam. You have to write down all the formulas. Get remembered. You had seen one of you kept your efforts continuously till you are the only student who is attending the online till the last class. Okay. I will share the analog electronics notes and today tomorrow's notes in here. That particular thing. Okay. Don't worry. Okay.
Thank you,
And
sir.
already all these notes these are all gate problems only. You don't have the gate problems solutions. Selvan,
Yes, sir.
you don't have the gate problems notes actually.
Sir, I'm having, sir.
And one more important thing, what is your opinion on my classes? Any feedback? What is the final opinion? Okay,
Sir,
Selvan. Yeah, boli. Yeah, tell me.
sir, I can understand the concept, sir.
Super. Problems also, because my way of teaching in online is quite different from other faculty. I am going to teach you in a neat, elaborate manner, because each and every average student also will listen the class in a efficient manner. Okay. Hope that, and all the best for your examination, Selvan.